efficient backbone design for fast instance segmentation. Problem overview. Instance segmentation requires both lightweight accuracy and real-time speed. However, FastInst uses ResNet 50 backbone, which adds latency. So our goal is to improve the trade-off between speed and accuracy. How it works: FastInst first extract features using a backbone, then a pixel decoder enhances them, and a transformer processes these features for classification and mask generation, and finally produces segmentation masks. And our approach: we replace ResNet 50 with efficient VITB1 here, a lightweight backbone to improve speed. We keep the rest of the model unchanged and test two variants, learnable and sinusoidal positional embeddings. For implementation, we use PyTorch and Detectron to train all models on Coco 2017 with the same setting, and run experiments on an HPC cluster. Speed is measured separately for accurate comparison. Results. Efficient VIT significantly improves speed up to 6 times faster, but accuracy drops a lot from about 35 AP to around 13-16. So we clearly see a trade-off: higher speed, lower accuracy. In training, our training is stable, so the issue is not optimization, but the backbone design. In conclusion, efficient VIT is promising for speed, but we need better integration to maintain accuracy. Thank you.
From a data-centric perspective, small objects are harder to segment because they occupy fewer pixels and are underrepresented in the dataset. So instead of modifying the model, we asked, can we improve performance by just changing the data distribution? Our hypothesis is that increasing small object examples will help the model learn better representation. We define small objects as those with area less than 32 by 32 pixels. We identify all images containing at least one such object. Then we created two datasets. One is with full oversampling, where all such images are duplicated, and partial oversampling, where only some are duplicated. Everything else stays the same, so we isolate the effect of the data. Full oversampling improves small object AP from 0.65 to 0.77. That's almost about an 18% gain. But the overall AP drops slightly, showing a trade-off. Looking at the object scales, full oversampling improves small object performance while keeping the large object performance stable. Partial oversampling reduces performance across all scales. This shows that the data distribution directly controls what the model prioritizes. Qualitatively, the base model often misses small objects completely. Oversampling helps recover some of that, but also introduces noisier masks and false positives. So it improves detection, but doesn't fully solve representation limitations. The key takeaway is that data-centric methods can complement the architectural changes. We can guide model behavior by changing the data it sees. It helps improve specific regimes like small objects. Next better step would be loss reweighting to get these gains without hurting overall performance. Thank you.
Okay. Hi, everyone. What I worked on for this project was a backbone replacement. Specifically, I swapped out FastInst's default ResNet 50 backbone with ConfMix Tiny to see how it changes the accuracy and speed trade-off. I'll walk you through why I picked this backbone, how I integrated it, and what the results look like. So the Since we were already exploring efficient VIT, which is a fast, lightweight, attention-based backbone, I wanted to find a third entry point, something that sits between ResNet 50's accuracy and efficient VIT speed, but with a different kind of architecture. So ConvNeXT Tiny is a purely convolutional network. It uses depth-wise convolutions and layer norm, modernizing the classic ResNet design without any attention. At 28 million parameters, it sits right between ResNet 50 at 44 million and efficient VIT's 7 to 14 million range. And it has strong ImageNet pre-training available through TIM, which meant I didn't need to source a custom checkpoint. Yeah, and the design of Res2 through Res5 maps naturally onto what Detectron 2 and FastIn's pixel decoder expect, which made integration easier. So moving on to implementation, I wrote a ConvNeXT backbone class that wraps TIM's feature extractor behind Detectron 2's standard backbone interface. The key point is that forward returns the same dictionary format and that the efficient VIT wrapper uses, so FastIn's pixel decoder didn't require changes. And the 4 output levels expose strides of 4, 8, 16, and 32, with channel widths of 96, 192, 384, and 768. I registered it through Detectron 2's backbone registry, so you can swap it in just by setting model backbone name in the config. Okay, looking at the numbers, ConvNeXT Tiny achieves an AP of 18.43, which is the highest among our other backbone replacements. Both efficient VIT variants come in lower on this metric, but clearly the trade-off is speed. So ConvNeXT Tiny runs at about 4.8 FPS, which is actually lower than the ResNet 50 baseline at 5.9 FPS. And the efficient VIT variants are much faster, 20 and 36 FPS. Yeah. So ConvNeXT Tiny is the best accuracy per parameter choice, but it doesn't close the gap with, oh yeah, it's the best accuracy per parameter choice among like the replacement backbones that we tried, but it doesn't close the gap with the ResNet 50 baseline. Yeah, which could partially be how I implemented the training. Okay, so now moving on to our analysis and takeaways. To summarize, ConvNeXT Tiny integrates cleanly into FastInst with no changes to the pixel decoder or head, and it outperforms both efficient VIT variants in AP and is particularly strong on small and medium objects. And the main trade-offs are that it's slower than efficient VIT. It sits at about 4.8 FPS, and there's still a gap to close against the ResNet 50 baseline, which could be due to like my training recipe issue. For future work, I would want to tune the learning rate and warm-up schedule specifically for ConvNeXT Tiny, as well as explore ConvNeXT Small as a higher accuracy variant, and also kind of like investigate what is going on the low level and profile where the FPS bottleneck is relative to the ResNet 50 baseline. Okay, that's it. Thank you. Thank you for listening.